nanoHUB-U, online instruction.
Welcome back to Unit 3 of our course on quantum transport. And this is the 10th lecture, so it's time to sum up what we have been doing. Now, as you know, our interest is in describing current flow through nanoscale devices, where this channel has certain energy levels and electrons are injected from a contact and picked up at another contact, giving rise to current flow. And one of the points I've stressed, especially in part A of this course, is that what makes transport difficult is this mixing of two very different types of processes. What you might call the mechanical ones, which are driven by force, and the thermodynamic ones, which are driven by entropy. And so when you're trying to describe transport, it's not enough to have the mechanics, like Newton's law for classical mechanics. You have to add these entropy-driven processes to it. And in the semi-classical context, Boltzmann showed us how to do that in the 19th century, and that's Boltzmann. And this Boltzmann equation is the centerpiece of all semi-classical transport. In part B of this course, what we are interested in is quantum transport, where for the mechanics, instead of Newton's laws, we have the Schrödinger equation. And what I'm trying to introduce to you is the part about including these entropy-driven processes to get this non-equilibrium green function method, or the NEGF. And so in Unit 1 of this course, we started by just talking about the Schrödinger equation itself. And this is something you might have seen in other quantum mechanics courses that you have taken, because that is described in all standard courses. What is non-standard is the rest of it. Although one thing we did in Unit 1 is introduce this tight binding model, which you may or may not have seen earlier, where we showed how you can write this H in the form of a matrix. But Unit 2, what we went on to is how to include the contacts. And there the first point was to recognize that these contacts require these additional terms, the sigma 1 and sigma 2 called the self-energy, and then there's the source term, electrons coming in, that's this S. And the resulting Schrödinger equation kind of looks a little different from what you would normally see. Normally just see that much, but you have these additional terms that you have to put in. And then I made the point that with electrons, the observable quantity is this psi-psi dagger. And so it is convenient to work with equations where the basic quantity is the psi-psi dagger. And these are the NEGF equations. And in Unit 2, I guess in lectures 2 to 5, we obtained these equations along with an expression for this current operator on how to calculate the current. And this is the general expression for the current. And for coherent transport, which is a subset of the problems we want to consider. So coherent means the only sigmas are associated with the contacts, and you ignore all interactions within the channel. That's coherent transport. In general, of course, we are interested in non-coherent transport, where you also include the interactions, which we'll be talking about, which we have also talked about actually. But for coherent transport, you could simplify this equation into a different form that's convenient. So where you have this current written in the form as proportional to F1 minus F2. And this is often called the transmission. But I'd like to stress that this only applies to coherent transport. You cannot use it in general. It's this one that you should be using. And more generally, you have this current operator, which you could use for all kinds of current. Anyway, so this is all things we did in Unit 2. And another thing I introduced then was also the physical interpretation of different quantities. That in order to keep your sanity and keep track of all these symbols, it is important to have a physical picture in mind as to what these things represent. Like Gn is like electron density. This A or spectral function is like the density of states. This is the in-scattering, that's like the broadening, and so on. Now, in order to use these equations, of course, first you need the H, which we did in Unit 1. But the next you need is the sigmas. And for the sigmas, in Unit 2, we talked about an elementary way of writing the sigma, which applies to one-dimensional problems. What we did in Unit 3, in lectures 3 and 4, is introduced a more general expression for the sigma, something you could use in general for many types of problems. Whereas this one is very special, applies only to the 1D case. And in Unit 2, we use this resonant tunneling as an example of how to use this method. And what we showed in Unit 3, in the second lecture, was how you could use this elementary method, but for a more difficult problem, a two-dimensional conductor. And this is a problem of great interest in its own right, because, as I've mentioned before, one of the seminal results of mesoscopic physics is this quantized conductance. The idea that when you take a narrow conductor, as you make it wider and wider, the conductance doesn't increase linearly, but rather it increases in steps. And this is a result that should come out naturally from the general NEGF method that we are talking about. And I always suggest this as a good example to try out yourself, because you have to do everything right in order to come out with results as clean as that, where you have this nice quantization. This axis is the width of the conductor. This axis is the transmission at a given energy. And this is a very good test example to try out. Because I always say, whenever you have a new method, first you should do a standard problem and make sure you get the standard results before you do complicated unknown problems. Now, next we talked about this general method for getting the sigma, and as an example of that, we said we could analyze ballistic conductors in graphene or in carbon nanotubes. So I guess this result is for graphene. And again, if you have set up the method correctly, these should come out automatically. As I've often stressed, the power of this method is you can do the calculation without necessarily understanding all aspects of the problem, as long as you are competent and you are setting it up properly. And then you can use your calculations to improve your understanding. You could say, well, why is the step at this energy? How do we understand that? So that way you can understand it. Use this to improve your overall understanding. Another example that we then talked about is this Hall effect, which involves this transverse resistance. And it's calculated at a given energy, like where the electrochemical potential is at low temperatures. And this axis is the magnetic field. And at low magnetic fields, it kind of goes linearly. That's the classic Hall effect. And at high energies, you have these amazing quantization, which was again another of the seminal results of mesoscopic physics that dates back to 1980. But if you have set up the problems correctly, these should come out automatically, right? So this is what we discussed in lecture 5 of this unit. That was lecture 6. Now, all of these problems, however, are examples of what you might call coherent transport. But the real power of the NEGF method is that it also allows you to include interactions. You see this through this sigma 0. So the sigmas, you have sigma 1 and sigma 2 due to the physical contacts. But then electrons going through the channel interact with the surroundings, and that can be described through these sigmas, the sigma 0 here. And how do you evaluate that? Well, you could use this same expression to come up with an expression for sigma 0 or sigma 0n or the gamma. Because the way it works is, you see, gamma is tau A tau dagger. A is supposed to be the surface spectral function or the surface density of states of the contact. But when it comes to scattering processes like this, you could view it as if the conductor is its own contact. That is, as if you have taken the conductor and connected it to a replica of itself through the scattering potential, the taus. And so you could write the resulting gamma 0 as tau A tau dagger, but the A is now the density of states of the conductor itself. not of some other physical contact, but it's the same A. And the tau and the tau dagger then, that product is what we call the D. And it's a more complicated object than tau in the sense that these are matrices with two indices. Here when you look at the product, it has 4 indices. It's a 4th order tensor. And this D then describes this strength of the scattering process, which is reflected in these taus. So this is what you'd get if you had elastic scattering. And again, as I pointed out, there's a lot of physics you could cover considering elastic scattering processes, meaning ones where no energy is exchanged. And so the energy, the sigma in at a particular energy depends on the electron density at that energy. On the other hand, what we did is in lectures 7 and 8, we talked about how you could extend this to include inelastic processes, where the in-scattering at energy E depends on the electron density at E plus h bar omega. So that would be like an emission process, as if a phonon got emitted and the electron went from that energy to this one. And these integrals runs from negative to positive. The negative part takes care of the absorption processes. Those are the minus h bar omega. Now, one of the points I want to make here is that everything we have done here is based on this one electron picture. That is, the way we think of it is scattering processes give rise to a certain random potential that an electron feels, which goes into this one electron Schrodinger equation. And then from this UR, you can get these taus, and accordingly you can get the Ds. Now, this one electron picture actually gets you the right results for elastic scattering. For inelastic scattering, as I made a point, there are some subtle issues that you have to think about, and that's related to this exclusion principle. Because normally, this is not a very obvious thing, right? And those are subtle issues that we discussed when we talked about it in this, I guess, lecture 8. Now, the standard way of obtaining these results is using this many-body perturbation theory, which requires this advanced second quantized formalisms, which we haven't talked about. Okay? And of course, the power of this is in general that it allows you to go to much higher orders. For example, given any specific interactions, you could write down higher order results. That is, this is like the lowest order where sigma is proportional to g. You could write a next higher order which would have g squared, 2 g's or 3 g's and so on. And this gives you a systematic way of writing all these interactions to any desired order. But for the lowest order, which is usually called the Born approximation, what you're using is the self-consistent Born approximation. In this order, you can write the results more or less intuitively from the one electron picture, though you have to be careful about these exclusion principle related subtle issues. Now, one important problem that often people worry about is this electron-electron interaction. As I mentioned, this is a very subtle kind of interaction where momentum is not relaxed, because what momentum one electron loses, another picks up, but phase is destroyed. And often, standard conductivity or mobility is not affected by phase relaxation, it's only affected by momentum relaxation. And so electron-electron interactions do not have a direct effect. On the other hand, there are many other transport problems or experiments which are phase sensitive. And so it is important to include phase relaxation without momentum relaxation. But to include electron-electron scattering from the first principles, that's much more complicated. See, what you could do is adopt a phenomenological approach. And this is what we talked about in lecture 9, where we showed that if you had a wire with a scatterer, if you do the coherent calculation, you get these oscillations in the potential, the electrochemical potential around the semi-classical value. And these coherent oscillations, of course, would usually be destroyed because of this loss of phase, the phase relaxation. And once you include this phase relaxation, you indeed get a curve, this black curve, where these oscillations have been suppressed. And how did you do this calculation? Well, not by including electron-electron interaction from first principles, rather by adopting a phenomenological approach. That is, we used a D which had this form. And in this form, it destroys phase but doesn't destroy momentum. On the other hand, if you used a D of this form, which is diagonal, it destroys momentum as well. And this is again reflected in this results. You see here, the oscillations are gone, but this part is flat because this is a ballistic region with no resistance, and so the slope is 0. On the other hand, once you include momentum relaxation, even this part there is a potential drop, and so there is a slope to it. Now, another case where people need to calculate these potentials is this self-consistent potential due to charging effects. And this is again part of standard device analysis, that you have to include the potential U due to the change in the electron density. And usually that's calculated through the Poisson equation, or what you might call the Hartree approximation. But in general, for small conductors, it's often important to include these corrections for exchange and correlation, these many-body effects. And again, the way you try to calculate these terms is using this many-body perturbation theory. Although there are approaches where you go beyond that, do something different. But the point is, this of course is a very vast field in itself. And in order to follow that, you need to understand this many-body formalism. But one point I wanted to make is that people often think that this is general, so it should be able to handle anything, the many-body perturbation theory. But what I'd like to mention is that there are many problems where this perturbative approach is not the best, doesn't give you the best results. You really should use other methods, non-perturbative approaches. And one example of this is this Coulomb blockade phenomena, or single electron charging effects, which are observed and which is a vast field of research on its own. And these require non-perturbative methods in general. Now, overall then, the point I wanted to make is that these basic NEGF equations and this current operator, in this course, we obtained them from the one-electron Schrodinger equation using this one-electron approach. And whereas commonly, they are obtained from this many-body perturbation theory. And these equations then you could solve to obtain the current for a given applied voltage once you know H, sigma 1 and sigma 2. This is what you might call coherent transport, where the sigmas are associated with the contacts. In general, though, you need to include interactions. This is this U, the charging energy, then this sigma zeros, which could describe elastic processes or inelastic processes. And these have to be calculated self-consistently in the sense that they depend in turn on the Green's function and the electron density matrix inside this. And so it's like you should make some assumption, calculate this, feed it back again, recalculate, and keep doing this till the whole thing converges. And in general, in device analysis, people always solve the transport physics self-consistently with the Poisson equation. And this is a more generalized version of that, you could say. And how do we write down what are these self-energy equations? Well, in some cases, you can get it directly from the one-electron approach, especially if it's elastic. If it is inelastic, then there are subtle issues like, as I mentioned, involving the exclusion principle. And of course, the formal way of getting those results would be from this many-body perturbation theory. But you can kind of, once you know the results, you can kind of rationalize it and understand where it comes from. There are other problems where you actually need this many-body perturbation theory in order to write down these self-energy functions. But then, of course, as I mentioned, there could be problems that require non-perturbative techniques. And so you might have to go beyond this. But one last thing to mention here then is that you see, in general, these equations are obtained from many-body perturbation theory. And so, in people's minds, this whole approach is kind of tied to the many-body perturbation theory. And so people view NEGF as an esoteric tool, which is accessible only to those who are well versed in this formalism. But the point I wanted to make is that there are many problems of interest these days where you do not really need to calculate the sigmas using this, because the kind of sigmas that capture the physics can be obtained more or less from the one electron approach. And so this part, I feel, should be much more widely known. It should be part of all graduate and even undergraduate curriculum. See? And this is and in that case, you see, you'd be able to do all kinds of problems that are of current interest, for example. And this isn't happening because in people's minds, again, this equation and everything is kind of tied to this very advanced formalism. Whereas ideally what should happen is, you see, this should be something that should be widely known. And the part that needs the advanced formalism would be certain types of scattering processes. So for example, the Boltzmann equation I had mentioned is the centerpiece of all semi-classical transport. Now in the Boltzmann equation, there's something called a scattering operator. Now how do you calculate the scattering operator? Well, those methods have evolved. They often use this Fermi's golden rule, something that was not even known in Boltzmann's time. But the basic Boltzmann equation, is still used. The scattering operator, how you evaluate it, that has continued to evolve. The same here. These are the basic equations. How you calculate these sigmas, how you calculate the self-energy, that will evolve. And as I said, some methods might even require non-perturbative techniques, etc. Well, with that then, I guess we can close up this unit, and we'd end with one more unit in this course about spin transport, which gives you a very good example of great current interest where you can use the formalism that we talked about, this NEGF method, which I usually don't refer to as NEGF method, but rather say that, well, it's just a basic method for contacting Schrodinger, for adding contacts to the Schrodinger equation. And in the next unit, I guess we'll be presenting examples involving spin, which I believe give you a lot of insight into the nature of quantum processes and how they differ from the semi-classical picture. Thank you.